Okay. So.
Okay, we see your presentation, please.
Okay, thank you. Good day, everyone. Thanks for being today here. My name is Paulo Reda, and I will present the work titled as Method for Distributed Detection Malicious Activity based on analysis of execution behavior. The growing number of malware threats in recent years is alarming as attackers increasingly use advanced masking techniques and avoid techniques, and these methods make malware harder to detect and remove, putting both as individuals and organizations at greater risk of security breaches. The malware today has become highly adaptive, and one of its most dangerous characteristics is its polymorphic nature. This means that it has the ability to modify its own code during execution, effectively change it itself to avoid detection. And this adaptability creates a significant challenge for traditional security system and approach of its detection. To evade detection, malware developers use masking techniques or avoid techniques which help the malware remain undiscovered. And this paper examines malware that employs anti-emulation techniques and polymorphism. Anti-emulation enables malware to detect when it's running in the emulated environment, suggesting the presence of the antivirus software that actually causes to stop doing some malicious actions. And obfuscation allows the malware to alter code for changing its behavior and helping to avoid detection by static analysis tools. And the main purpose of this work is to present an approach for analyzing an infected program's behavior with the modified isolated environment for detecting the presence of the malware activity. Okay, so for malware detection, two widely adopted concepts in malware analysis are recommended. Emulation and sandbox technologies. Emulation technology simulates the execution of low-level instruction, enabling examination of malware behavior. And meanwhile, the sandbox environment create the isolated settings that ensure that safety of executing malware, preventing potential harm to the host system, while allowing for detailed analysis of malicious activities. The developed emulator incorporates emulation of 4 sets of registers used for different purposes, such as primary pointer register, string register, and general purpose registers. Additionally, it emulates the program memory, which is crucial for executing programs. All these components can be classified as active components from point of view of executing the programs. And it is because their state is changing while the program is executing or low-level instructions being doing on the central processing unit. The proposed modified isolated environments utilize parameters derived from analyzed anti-emulation techniques. These parameters enable the sandbox to generate environments that respond differently to the anti-emulation techniques employed by malware. Consequently, the behavior of infected programs may vary when executed in different isolated environments. Any differences in their behavior during execution suggest that the analyzed program is infected. The developed application facilitates isolated instructions execution and incorporates 3 main modules: the communication module, emulator control module, and analysis module. The control module records changes in register values during the program execution, while the communication module enables users to submit programs for analysis. The application structure is illustrated on the slide. Okay, regarding values from the registers, as indicated in the analyzed articles, is possible only through the use of software interrupts. When these interrupts are invoked, the CPU releases the values stored in registers, transferring them into the program memory. Since the program memory is also emulated and presented as an object, program object, the sandbox can access to and read these values that contain it. Since the proposed method requires the use of multiple isolated environments, it is advantageous to implement a computing system that distributes the execution of infected software across several computing elements. This system employs a central server that collects execution result and makes decisions regarding the presence of malware activity based on the behavior of the analyzed programs. The proposed system can be characterized as a centralized and heterogeneous grid computing system, and the central server acts as a tool for users to submit software samples for malware activity analysis. Computing elements received parameters for generated isolated environments and executing the programs. And after that, the central server also manages task execution across all elements, and the system structure is illustrated on this slide. Okay. To identify malware based on analysis components, the identification process is proposed to be performed using the two key parameters. It is a difference in productivity computing and presence of non-similar behaviors. In order to evaluate productivity, the central server collects data about the computing nodes and benchmarks it against test tasks. While performing execution in isolated environments, central server will generate two sets of parameters, where B is a set of behaviors that related to one infected software, and K is productivity coefficient. To detect the presence of the malware activity, it is proposed to use next two rules that describe that we have spoken earlier. Okay. This study realized a system that used 4 computer nodes. First row demonstrate what parameters were used in order to generate isolated environment. And as a result, it was developed 8 samples of artificial created viruses or malwares. And malware models first, second, third, fourth, and eighth were successfully detected due to the distinctive behavior when executed under different conditions. About model 5, it is demonstrated the same behavior across all nodes, despite the presence of parameters designed to trigger changes in behavior. Specifically, nodes 2 and 3 containing the necessary parameters that should have caused the usage of the code transformation after detecting emulating environment. However, the behavior remained unchanged, suggesting that the program might have employed a pause strategy. Model 6 was misclassified as safe by the system because its behavior and performance coefficient apparent to the common to the expected norms. On the other hand, Model 7, which did not incorporate any evasion techniques, displayed a consistent behavior across all the system. Okay. Conclusion. The suggested approach demonstrates the potential to detect malware activity based on different in execution behavior. This method can be used to detect malware that employs anti-emulation techniques and polymorphism. To improve this method, it is essential to address the following primary tasks. The first one is consider the optimal approach to distribute tasks across different computing nodes. The second one is analyze and implement new evasion techniques used by malware. Thanks for your time and attention.
Thank you, Paulo, for your interesting presentation. Dear colleagues, any questions? So I have one question. What is the limitation of your approach? Which may be some drawbacks which is to be fixed to improve?
We need to improve the problem one problem here is that we use only known anti-emulation techniques, and with this we can create rules that alters the behavior of isolated environments. So as more studied new anti-emulation techniques will be, the more better this approach will be.
Okay, thank you.